Well, hey everybody, it's second semester, so I thought I'd remind you about our materials that we need to have. Make sure that you're in a quiet place or that you've got some headphones so you can kind of tune out any distractions. You either need to have your note sheets with you that I've provided or that you're taking notes in your notebook. Make sure you've got your graphing calculator because this first standard we're working on is on the graphing calculator, so you're going to want to have that handy. And make sure that you're actually ready to watch and take notes. Don't forget you can pause whenever you need to, or rewind and go back and listen to something again. So let's go ahead and get started. All right, our first standard for Chapter 7 is going to be about graphing and identifying key characteristics of rational functions. We finished first semester with rational expressions and equations. Those were the polynomials that were written in a fraction. But we're going to be working at the graphs of them this time. So this one's going to be all about gathering the information about the rational graphs. So that's what we're going to be starting with, is just getting some information, not physically graphing them. So let's go ahead and begin. All right, so we're going to start with two different parent functions. And if you've got your graphing calculator, it might be helpful just so you get used to entering these in. So grab it. If you need to pause, go ahead and do that. If you've already got it, here we go. So go to the y equals, and I want you to type 1 divided by x, and it's just going to look like 1 slash x, and that's how we get this. And this is the parent function. That means that no transformations at all have happened. Press the graph key, and if your graph doesn't come up centered at 0, remember you can try zoom 6. Zoom 6 is the way we get to reset your screen. So zoom 6. And what you should notice is you should have two pieces to this graph. One that does this and one that looks like it's coming down this way. So this is the parent function of 1 over x. Now I want you to go back to y equals, and instead of having x, I want you to type in x squared. So you can just leave the x there and then hit the exponent button, and it'll still look like 1 slash x squared, but then go ahead and graph that one. And you'll notice something completely different. It still has two parts, but one is on this side and the other one is on this side. Now you may think that eventually, well, that's kind of a bad drawing, eventually they will touch each other, but what we're going to learn is that they will never touch each other. They will never actually meet up here as this goes up towards infinity. These two pieces, what we're going to call branches, the branches will never hit each other. They will never actually touch. All right, so these are the two kind of parent functions. And you can imagine that if we were to use a negative sign, that we would flip them over. And that's one of the things we'll be working with. Otherwise, we're going to be shifting them left and right and up and down. And that's going to come in the next video. So we're going to be discussing the domain and range, and we're going to be talking about something called an asymptote. Some people pronounce it you can pronounce the P and the T as an asymptote, but most often it's just pronounced asymptote, where the P and the T in the middle are almost silent. All right, so let's go ahead and talk about the domain and range. So if I go back to the original function of 1 over x, and this is where we had a piece down here and a piece up here. What we notice is that the values are kind of hovering around the y-axis and the x-axis, but they're never actually touching the x and y-axis. And that's actually the truth. Because of what we call asymptotes, I'm going to change my pen color. If you've got a highlighter, that might be useful. So this here is a vertical asymptote, and this one is serving as a horizontal asymptote. And that asymptote is a line that is not being crossed or doesn't appear to be crossed. And that is because, well, I would say that x cannot equal 0, which means it changes my domain to be from negative infinity to 0, excluding 0, and then on to positive infinity. So that's my domain. Well, you can see that my y values also are not crossing this axis here. So we would say that the range also would be from negative infinity to 0 and union from 0 to positive infinity. The reason that the range is restricted, if my domain is not allowed to be x in this case, I can put really, really small numbers in here, and I could put really, really, really large numbers in my denominator. But the truth is that this fraction, 1 over something, as long as I'm dividing by something, it will never be 0. So my outcome will never be 0. It'll be a really small number that it's close to 0, but it'll never actually be 0. Well, let's take a look at the domain and range for the x squared, 1 over x squared. So this is the function 1 over x squared, our parent function. And here we can see again that I'm not allowed to put 0 in, so my domain is the same as it was for the other one. And then I go to 0, excluding 0 to positive infinity. But my range is different. I have absolutely nothing below my x-axis. My y values actually do not go below this axis, which means that my range is going to be slightly different. My range is from 0 to positive infinity. And I'm not including it because, as we know, no matter what number we put there, I'll never have a fraction that equals 0. Okay, so my range in this case is from 0 to positive infinity. So we're going to talk about the intervals of increase and decrease. And I'm going to again draw the same graph. So this is my f of x equals 1 over x. And if we're talking about increase, everyone wants to tend to think that increase happens when the graph goes up. And that's not entirely wrong, but it is when the graph has a positive slope. That is that as you move, as you're traveling and going in this direction, that's when the numbers are getting bigger, that the y values are growing. But so if we can take a look here, that as we move this way, my y values are actually getting smaller. Then they take this giant jump and they start at positive infinity, but again, they're getting smaller. So I actually have no intervals of increase and decrease. Or, excuse me, no intervals of increase. However, we can say that this is always seemingly to decrease, so this is always decreasing. Because as we move, these values keep getting smaller. And although they start really high, as we move across, the values are getting smaller. So let's take a look at this one. This was our 1 over x squared graph. Write that again. And as we move across, and as we go from the left to the right, it seems like those values are getting bigger. So we do have an interval of increase. And then they're going to start way up here at positive infinity, and then they're going to fall, which means that we have an interval of decrease. So let's write that down. So our interval of increase is occurring from negative infinity to 0. And our interval of decrease is occurring after 0 and on to positive infinity. So that is that as we're traveling this way, the numbers are getting bigger, but all of a sudden, the numbers start getting smaller. So that is the intervals of increase and decrease. All right, and the last piece of this one, lesson, in trying to gather some information about my graph, is about whether or not we have an even or an odd function. And what's interesting about this is that it doesn't have to be even or odd. It can be neither. So it's important to know that there's a third option if it doesn't fit even or odd. So I'm going to start on this side with even. And what you have to notice that this is nothing to do has nothing to do with the exponent. Okay, it also has nothing to do with whether or not there was a 2 or a 4 or a 6 or a 7. It has nothing to do with what we consider even and odd numbers. What it has to do with is the shape and the symmetry in our graph. So even functions are if when you have f of x, it is the same outcome as having the f of the opposite number. And I'm going to make a little table of values. I think this will make more sense. So if I have some x values, -3 and +3 and -2 and +2, if the outcomes, if the y values are the same, that is if I have a 4 here and a 4 here, and a 2 here and a 2 here, okay, whatever function this happens to be, that means that they are symmetric. Okay, so we can see that if it's x is -3 or +3, the outcome is the same. This is an even function, and that means that it is symmetric over the y-axis. Okay, it is symmetric over the y-axis. So for example, this is an even function because if I'm on this side at x equals, let's say, 2, or I'm on this side at x equals -2, the y value is the same. This makes it even. So it has to be symmetric over the y-axis. And if you see reflection, then this is an even function. Okay? Now, odd functions. Odd functions are that if you have f of -x, it's equal to the opposite of f of x. And this one's a little trickier to picture. So I'm going to again make a table of values to help explain. So if I have 2 and I have -2, that means I could have a +1 and a -1. So they have to be opposites. Now let me do another example. If I have +1 and a -5, then I have -1, I should have a +5. That is that the x's and y's are opposites of each other. And it doesn't, that the opposites of the x's are the opposites of the y's. This is very tricky. So please look at it again. That if I have a +2 gives me a 1, that my -2 has to give me a -1. If I have a +1 that gives me a -5, then the -1 gives me a +5. So hopefully that right there helps a little bit with this one. This one's a little bit harder to picture on the graph. And one of the ways to picture it is that if I have, let's say I have a -2 here and that produces a positive x, or a positive y, that my +2 will produce the same -y. So it becomes this opposite thing. So I could do it again. I could say I have a -3 over here, which gives me a -1, but if I have a +3, I have to have a +1. So you can see what happens is you get this shape perhaps, and this makes it an odd function. It doesn't have to be this shape. There could be a lot more to it, but if you can follow this pattern, then it makes it an odd function. But not all functions follow either of these rules. So if you notice that it's not symmetric over the y-axis, evens, then just say that it's not even. And if you notice that you're not getting the outputs to be opposites as in the odd function, then it's not odd, which leads it to be neither. We can definitely talk about this one more together. Okay, but it has to fit either one of these or it has to fit none, and which makes it neither odd or even. So again, it has nothing to do with the exponent and has nothing to do with we understand to be odds and evens. All right, we're going to get to practice more of that together in class. Great job.